This is, what is the probability that I get at least 2 6s? So at least 2 6s. So at least means what? So x is less than or equal to 2, and x is at most 7 6s.
X is greater than.
No, at most. Oh, it's greater than, yes, greater than, thank you. I think I said greater than, wrote less than. Okay, so x is greater than or equal to 2, and x is less than or equal to 7. So at least means greater than or equal to, at most less than or equal to. Okay.
You write it as like 2 is less than or equal to x is less than or equal to.
Okay, so yes, another way to write that is 2 is less than or equal to x is less than or equal to 7. They're the same thing. That's from algebra. Okay, so, all right, so that's, could I use the same type of, could I use the commands from the other page and just add them up? I mean, isn't that pretty easy? So I could just do binomial, what? Would I want to do PDF or CDF? I don't think I do.
PDF.
Doesn't this mean the probability that x equals 2 plus the probability that x equals 3 plus ... the probability all the way up to x equals 7? And this is out of how many 6s? How many times am I rolling the die?
7.
No.
Rolling the die.
I'm rolling the die how many times? 30.
30.
So between 2 and 7, wouldn't it be easier just to do the PDF one and add up the 2nd, 3rd, 4th, 5th, 6th, and 7th? See, the cumulative keeps adding them all up, and if even like when you go to the 7th one, hasn't that included the 1st and the 0 one? See, the CDF isn't going to be valuable here. Binomial CDF, no, is not going to work. Because that has all of them added cumulatively. You don't want to, so if you wanted everything less than 7, it would be good.
Could you just subtract everything less than 2 from below?
You could, but isn't it just going to be easier to do binomial PDF and just add up the ones that it gives, and leave it open-ended and do like 30 comma 1/6? Okay, watch what happens. This is going to work. So second distribution, PDF, 30 trials, 1 divided by 6, and then leave the x value open. Okay, so what's this first one again? That is the probability that x equals 0. Okay, this is the probability that x equals 1. So where do I start writing? I start right here. So this is going to be 0.0733 plus the next one. This is the probability that x equals 3. This is x equals 2. The next one is x equals 3. So this is 0.1368. Do you see what's happening here? Does this make sense? Okay. PDF gives all the equal to ones listed out. So I want x equals 2, 3, 4, 5, 6, and 7. So I have 2, 3, and then I want 4, which is 0.47, and then plus 0.1921, that's 5, and then 0.1601, that's 6, and then finally 0.1098, that's 7. And then we just add those up. And really, I mean, that's about the shortest way you can do it. I mean, you can do like, you could do less than 7 and then subtract out less than 2 or less than 1, like Alexa said. That's fine, like we did in the notes last time. But now that we know that it'll list them out for us, this is just as easy. So 0.0733 plus 0.1368 plus 0.1847 plus 0.1921 plus 0.1601 plus 0.0198.
1098.
Did I type it in wrong?
I don't know. You said 01.
Well, it was 1601 is the one before it. Did anyone else get 0.8568?
Yes.
Okay. So 0.8568 is that probability. Okay, you just added wrong is all. That's all. Or copied something wrong. I mean, if you did the command, you should be fine. All right, so now, here's where have we talked about the normal model yet?
No.
Isn't the title of this section Normal Model to the Rescue? Okay, so basically, everything that we do is going to end up changing to the normal model for the rest of the year. So we'll learn something and then we'll learn how to change it to the normal. That's pretty much what's going to happen. Okay? Normal model, very, very important. Okay. All right, so suppose we're now, instead of rolling our die, how many times did we roll it in the last two examples? 30. Okay. And now we're going to roll it how many times? 1 million. So what's n in this problem? N is 1 million. And P is the probability of success. What's P? 1/6. I'm doing the same thing, only I have a bigger N. That's all. Same thing. So I want to know now what's the probability that X is greater than 167,000 sixes. Okay, again, I wrote down the N and the P. It's very similar. The X is the number of sixes out of how many rolls? 1 million rolls. Okay. So, and X is binomial, and N is 1 million, and P is 1/6. So, all the same stuff, write down the probability problem. What is the probability that X is greater than 167,000 sixes? Now, this is slightly different now. Greater than, it's not greater than or equal to, is it?
No.
So, this, my CDF will not calculate greater than. My CDF calculates less than, right? So what? Very good. 1 minus the probability that X is less than or equal to. Do I need to change the numbers, or can I keep it 167,000? Why can I keep it?
Because it's greater than, not greater than or equal.
Yeah, it's not included here. So it's okay if it's included here. Okay, so that would mean we're going to type in 1 minus binomial CDF, and then 1 million, comma 1/6, comma 167,000. So everyone should be doing that right now. Oh, what did I do? 1 minus. You got an error? Well, let's see what I get.
Yeah, I got it.
It's nothing to do with radians.
Is it too big? Or no, it has to be less than 1.
Does it say domain error?
Yeah. It says we say go to.
No, because I get an error too, and everyone should get an error, because you have too many trials for the binomial distribution to handle. Okay, the binomial distribution can't handle this. So this has no solution.
Yes.
No solution with binomial. With binomial. Okay, this is not going to have a solution with the binomial distribution. Okay, and that's just because your N is too big. Too big. So, we go down to the next paragraph. In many cases, it's useful to approximate a discrete distribution. Discrete meaning you can only have whole number values of things. I can only roll whole number values of sixes, okay? With a continuous distribution. Continuous distribution, all values on the number line. We talked about this a long time ago. Discrete distribution, shoe size. Continuous distribution, foot length. Okay, there's a difference between the two. So we are going to estimate a binomial distribution, which is discrete, with a continuous distribution called the normal model. Okay? In particular, we often use the normal distribution to approximate the binomial. Historically, this is because we didn't have calculators with binomial CDF. But even our calculators obviously have limitations, correct? So even now there are some problems. Okay? Fortunately, the normal distribution approximates the binomial quite well in certain circumstances. Okay? So, I'm not going to do a bunch of examples here. So, this approximation works best when P is close to 0.5 and N is large. So, we're going to use the normal distribution. Okay, remember normal. What are the parameters in a normal distribution? Mu and sigma. So we're going to use a mu, we're going to find a mu and a sigma for a binomial, okay? So we're going to use this to replace the binomial of n comma p. All right, so we are going to take our binomial, we're going to transform it into a normal model, okay? So, does the binomial distribution have a mean? What is the mean of the binomial distribution? That's the expected value, yes. It's a formula from the last day of notes. All you have to do is look at it. N times P, or memorize it. Fantastic. And the standard deviation of the binomial distribution is NP and Q. So to change a binomial into a normal is actually very easy. You take the binomial distribution, you find its mean, and guess what your mean is? For when you change it to normal, N times P. And your standard deviation is the square root of N times P times Q. So you're changing the binomial into the normal using the formulas for its mean and standard deviation. It's pretty simple. Now, when is it best to do that? When is it okay to use a normal model to estimate a binomial distribution? When n is large. Is 5 large? No. So if you have n equals 5, you're going to do something 5 times, roll a die 5 times. You're not going to use the normal model. Okay? And at the same time, the probability of success should be close to what? 0.5. So these are the times this approximation works best when the probability of success is close to 0.5 and n is large. Is our n on our second one when it's 1,000,000, is that large? Now, is 1/6 close to 0.5 for a probability? No. So this may not be the best example to use to change. Okay, oh well. I don't even know if we're going to do this one, so. All right, we'll probably do a different one. Yeah, we're going to do a different one. Okay, so now the success-failure condition down here at the bottom. Okay, and this is basically really telling us when we can use the normal model. So if x is a binomial distribution of n and p, and this is the key, this is the big check to see if you can use the normal model, right down here. So it's called the success-failure condition. We're going to use it tons and tons. Okay, we're going to have to learn to do something called check conditions, because we're going to be changing from one model to another, so there's certain things we have to make sure that work out, and this is going to be a big one. So if x is a binomial, and n times p is greater than 10, and n times q is greater than 10, now n would be the number of trials. You know where the n is coming from? N is the number of trials. P and q are the probability of success and failure. If you take the number of trials times the probability of success and times the probability of failure, and they're both bigger than 10, then really that's all you need to decide that you can change it into a normal model. So then you find the mean and standard deviation of the binomial distribution, and that's your mean and standard deviation of your normal. So that is, it's okay to use the normal whenever the expected number of successes and failures are both at least 10. That's good. That's loud, and that's on the video too. I'm so happy. All right, so now, why NP greater than 10? So this is what's called, I call this a proof. Okay, this is a proof. Okay, does that mean that you're ever going to have to do this in your homework? No. Okay, this is a nice to know. A proof is why. Why does n times p and n times q have to be greater than 10? Why? Okay, so why n times p, and we're just going to look at greater than or equal to 10, if greater than. Okay, so n times p. N times q would be a similar proof. So if we want to use the normal approximation when p is close to 0, we should be able to go at least 3 standard deviations below the mean and still be in the domain of x. In other words, we shouldn't be in negative territory. Okay? So n times, basically they're saying if we're going to use a normal model for things like getting a number of 6s, we should be able to go, here's the mean, we should be able to go 3 standard deviations, and can you roll a negative number of 6s? No. So this third standard deviation over here below, or this third standard deviation over here should still be greater than 0, shouldn't it? Because you can't physically get a negative number of 6s. So basically we're just saying, in order for this to be reasonable to use a normal model could potentially have negative values, right?